Okay, today is day 2 of binomial probability, which is section 6.3 in your textbook. 6.3 covers 2 different types of probabilities. Binomial is the one that we're going to spend more time talking about. All right, first thing we're going to do as a review from yesterday, what does it take to be a binomial setting? Or what do you have to have, what conditions have to be met in order to use binomial probability? There's an acronym, BINS, B-I-N-S, binary. Each trial has to be able to be classified as a success or a failure. Independent. Knowing the result of one trial must not tell us anything about the result of another trial. N, the number of trials has to be set in advance. S, the probability of success must be the same on each trial. A couple other reminders. If you're asked to verify if you have a binomial setting or not for an AP question, make sure all of these things are addressed in context. Okay, second thing is the independent issue. If you are doing a problem where you're sampling without replacement, we have to make sure that we're not sampling more than 10% of the population. Okay, the formulas. This is how they appear in your textbook. The X is what we're interested in. How many successes for a particular situation. N is the number of trials. P is your probability of success. 1 minus P is your probability of failure. For this part in front, known as the binomial coefficient, there are 2 different ways or notations that are commonly used. This matches what your calculator does. This is actually how it appears on the AP reference sheet, or at least last year's AP reference sheet. Okay, the new thing for today, or one of the new things for today. If a count X has a binomial distribution with the number of trials N and a probability of success P, the mean and standard deviation of the distribution. Okay, now we talked about this, I don't recall this section precisely, but prior to today, if you're doing a probability distribution, that represents everything that could happen in a given scenario. So everything kind of fits that population as opposed to sample thing. So the notation that we use is the symbol for population mean, population standard deviation. A common mistake is students tend to use these formulas in places where they shouldn't be used. Make sure that you are only using these in situations where you are told or you've determined or you're assuming a binomial. They don't work in other places. Those formulas are on a reference sheet that you will be using or you'll be given when you take the test. All right, I guess we don't need to hash out this again. I already mentioned this on, oops, I'm sorry, I didn't see that. I'm not going to go through this again. I already mentioned it on the previous slide. A very common thing that happens in the real world of statistics is you're in situations that involve sampling without replacement. If you're doing a sampling without replacement, you have to make sure that you're not sampling more than 10% of the population size. All right, a recap of one of the problems that we did yesterday. Each child of a particular pair of parents has a probability of 0.25 of having blood type O. Suppose the parents have 5 children. Find the probability that exactly 3 of the children have type O blood. So, 5 trials, that's the N. Each time you have a kid, it's a trial. We're interested in 3 successes. That's the K. The probability of success is 0.25, happening 3 times. Probability of failure is 0.75, that's happening twice. This tells us all the possible combinations of which ones are the successes, which ones are the failures. So a little less than a 9% chance of that occurring. Should the parents be surprised if more than 3 of their children have type O blood? Well, in order to answer this, we need to know what's the probability of being greater than 3. Probability distributions are discrete probability distributions. It means endpoints matter. Greater than 3 and greater than or equal to 3 are 2 different things with discrete probability distributions. With continuous probability distributions working off of density curves, then that's a different story. So greater than 3 in this context means 4 or 5. So we have to use that formula twice. Once for 4 successes, once for 5 successes, and then get our final answer. Well, final probability answer. Going back to the should they be surprised, you're typically going to be using should you be surprised, thinking of that as an unusual event. An unusual event, the cutoff typically is going to be the 5% mark. If there's less than a 5% chance of it occurring, it's considered unusual. If there's less than a 5% chance of occurring and it's considered unusual, that means that's something you're surprised by. Okay. Now it turns out that we have some good calculator functions that can bypass a decent amount of the tedious computation that sometimes can be associated with these problems. All right, I believe this is another problem from yesterday. Suppose you are taking a 10-question multiple choice test. Each question has 4 choices. If you randomly guess on each question, what's the probability of exactly 3 correct? So, 10 trials, we're interested in 3 successes. 0.25 chance of success, that's happening 3 times. 0.75 chance of failure, happening 7 times, looking at roughly 25%. All right. On our calculators, zoom out a little bit here. If you go to second above bars as distribution, we were here and used normal CDF decent amount. If you scroll down, there's a binomial PDF and a binomial CDF. Okay, binomial PDF is used in a situation where we're interested in an exact number of successes. So in this case, exactly 3 successes. We're going to choose that. The number of trials, 10, each time we guess. Probability of success, 0.25. We're interested in 3 successes. Enter, and here's your 0.205. Now, we've also talked that in real-world settings, very often we're not necessarily interested in exactly one event. It's the type of thing like results at least as extreme as these. That's ultimately where this is going to be, or one of the places this leads to with inferential statistics. So summing up a series of probabilities is actually going to be something more common than finding the exact probability as we move through the rest of the class. So, talking about that in terms of how do we set it up, and then focusing on calculator keystrokes. Because when you get into summing multiple probabilities, it's highly unlikely you're ever going to do that by hand. So here's our scenario for the next set of examples. According to Nielsen Media Research, 75% of all United States households have cable television. So based on that fact, here are some probability questions we could ask. In a random sample of 15 households, what is the probability exactly 10 have cable? Random sample of 15, what's the probability fewer than 13? At least 11, and between 5 and 12 inclusive. So this one, we're interested in exactly one particular 10 successes. Fewer than 13 is everything from 0 to 12. At least 11 is 11 to 15. Between 5 and 12 inclusive, well, that's kind of obvious. So how do we interpret these? What are the calculator keystrokes? So part A, a reminder of the prompt. First question, in a random sample of 15 households, what is the probability exactly 10 have cable? Well, if we were to do this by hand, this is what it would look like. Calculator keystrokes. It would be binom PDF, well, binom part because it's binomial probability. PDF is referring to using exactly one as opposed to, or finding exactly one as opposed to a sum of them. Number of successes, probability of success, what are you interested in? It's kind of weird, this slide doesn't have the answer. Type that in real quick. So the distribution menu, same one that had normal CDF. We want binomial PDF. 15 trials, probability of success 0.75. We are interested in 10 of them. So their probability is about 0.1651. All right, part B. In a random sample of 15 households, what's the probability that fewer than 13 have cable? A reminder again, binomial probability is a discrete probability distribution. Endpoints matter. So fewer than 13 doesn't include 13. It's everything from 0 successes up to including 12 successes. Okay, the binomial CDF on your calculator, what that does is it sums from 0 up to whatever number you tell it. So when we type it in our calculator, binomial CDF, number of trials, probability of success, 12. If that's CDF as opposed to PDF, that's going to sum all probabilities from 0 up to including the 12, and that's what we end up getting. All right, part C from our cable TV scenario here. What's the probability at least have 11? At least 11 have cable. At least 11 means it could be 11, could be 12, could be 13, could be 14, could be 15. Okay, the important fact we're working off of here, from 0 to 15 is the entire distribution. That means from 0 to 15, if we add all those up, it has to equal 1. The CDF function only sums from 0 up to the number we tell it. So what we're going to do is we're going to start with the 1 and then take away the 0 to 10. So it'll be 1 minus binomial CDF, trials, probability of success, 10. So this will leave 11 to the end. Or in other words, it'll leave 11 to 15 for this particular problem. All right, next possibility that involves using the binomial CDF function. What is the probability that between 5 and 12 inclusive have cable? So what we're going to have to do here is subtract 2 binomial CDFs. What we're going to do is have the first one sum everything from 0 to 12, and then have the second one take away the 0 to 4. So binomial 15.7512. That sums everything, all possibilities of a probability from 0 to 12. Binomial CDF 15.74, that sums everything from 0 to 4. Well, this minus that leaves 5 to 12. So this is a screenshot of the older calculators. Not going to look exactly like that, but similar to it. All right, that's it as far as examples. Last thing, this is a similar type of warning or advice or whatever you want to call it that we had when we were using the normal CDF stuff. If you're using normal CDF, it's not good enough to just list the numbers. If you are going to be using that to show your work, which is valid by AP rubrics, you have to at least label the numbers in terms of what they stand for. So, for example, if you just have this without an indication of what those numbers stand for, you're not going to get full credit, perhaps no credit for that particular part. You can label them just as they appear on your calculator screen. Trials, probability of success, and you can even just use the P, it doesn't have the probability of success, and then the X value of the 3. This would be considered valid showing work. Now, a similar thing I said with the normal CDF, this is already an abbreviation. You can't abbreviate an abbreviation and get credit. So some people just put like BPDF on a quiz or a test. You're already getting away with the calculator doing a very significant amount in some situations of work for you, and it's already being an abbreviation to start with. Binom PDF, by the way, stands for Binomial Probability Density Function. Binom CDF would stand for Binomial Probability Cumulative Density Function. You're already getting a significant amount of abbreviation here. You're not allowed to abbreviate the abbreviation. All right, I think that wraps it up for today. I want to do a quick recap of what we did and then a lead into what we still have to talk about. All right, so we started off with what does it take in order to be a binomial setting? What are the potential ways the probability formula could look in order to apply this? It was on a different slide, but we talked about it here with the idea of very often in a real-world setting, using this binomial probability involves sampling without replacement. If we're going to be doing that, we have to make sure we're not sampling more than 10% of the population. Okay, this here, I'm going to come back to in a second. We reviewed, where was that slide? Seem to have misplaced that. Where did we start off with the blood typo one? Okay, I do not know where that is offhand, but that's okay. We reviewed a couple problems that involved, oh, here it is. We reviewed a couple problems as we solved them yesterday, and then we looked at, well, what are the calculated keystrokes to bypass a lot of the computation? Okay, lastly, we introduced these formulas right here. Okay, we talked about them and then didn't do anything with them. The main focus of tomorrow's lesson is we are going to flesh these out in more detail and why we need to know these for the small part of a bigger problem. But for today, that is it, I believe.